Dear students, in this section we can go through some of the basic ideas about magnetic field. We are already familiar with the magnets. The magnets have a wide range of applications, from the use in loudspeakers, electric fan, refrigerator door, to the high-end devices like MRI machines, etc. So in the previous section, we studied the electric field produced by the charges. Similarly, the magnets produces magnetic field around it. The magnetic field by a magnet has its origin in the intrinsic magnetic properties of a substance. In addition to the magnets, the moving charges or the currents also produce the magnetic field around it. We have a famous Orsted's experiment, that is when we doing the experiment in his lab, and when a current is flowing through a conductor, he noticed that the deflection of a magnetic needle placed near to the conductor. So, on a keen observation, he found that the deflection is due to when the current is flowing through the conductor. That means, in order to deflect a magnetic needle, there should be another magnetic field. That means, he concluded that when a current is flowing through a conductor, a magnetic field is formed around it, and this magnetic field is the reason for the deflection of magnetic needle which is placed near to it. Now, how can we represent a magnetic field? Usually, the magnetic field are represented by the magnetic field lines. Magnetic field lines. So, in the figure you can see the magnetic field lines which is drawn around a bar magnet. And the direction of magnetic field lines is from starting from the north pole to the ending at the south pole. So, if there is a larger intensity of magnetic field, then the number of magnetic field lines passing through that region will be high. If the magnetic field is less, the number of lines will also be less. Okay. So, the number of field lines through a particular area represents the magnetic field, the intensity of magnetic field or the magnitude of magnetic field. Here, the SI unit of how can we measure the magnetic field? Then, so the SI unit of magnetic field is the Newton per ampere meter. Newton per ampere meter. Is another unit is also there, that is Tesla. So, the Tesla, 1 Tesla is equal to 1 Newton per ampere meter. Now, we have another term, that is the magnetic flux. Magnetic flux, it is a measure of the total magnetic field passing through a given area. Total magnetic field passing through a given area. So in the figure you can see there is a here there is a magnetic field. It is represented by the magnetic field lines. Here the intensity of magnetic field is given by denoted by the letter B. Okay. So the magnetic flux that is passing through a given area is given by the expression phi is equal to B A cos theta. Okay. So B is the magnitude of the magnetic field and A is the area. So here the direction of the area, that is the which is represented by a line which is perpendicular to the surface. So that is the direction of area. So there is it creates an angle with the direction of magnetic field. Suppose theta is the angle between the direction of magnetic field and the perpendicular drawn to the area. then phi is equal to Pa cos theta. So that is the magnetic flux. That is the total magnetic field. So what is the intensity of magnetic field? So from this expression, we can see that the intensity of magnetic field is the normal magnetic field or the magnetic field lines passing through a perpendicular unit area. Okay, so that is the relation between magnetic field and intensity of magnetic field and magnetic flux. The SI unit of magnetic flux is the Weber. So the symbol is capital W small b. That is the Weber. Now we know the moving charge or the current produces magnetic field around it. Here the reverse of this process is also possible. That is, a varying magnetic field can induce the electric current in a circuit. A varying magnetic field can induce electric current in a circuit. That means whenever there is a change in the magnetic field associated with a coil, a current can be induced, a current can be produced in the coil. Okay, so that phenomena is called electromagnetic induction. It is called electromagnetic. It is introduced by Michael Faraday. He was one of the famous physicists, and he did a lot of interesting experiments. Okay, so the phenomena in which the electric current is generated in a circuit by varying magnetic field is called electromagnetic induction. Here you can see there is a coil is there, and the coil is the two ends of the coil is connected to a galvanometer, and when we insert a magnet, a bar magnet, inside the coil, you can see a deflection in the galvanometer. Okay, when we take out the bar magnet, there is also deflection, but in the opposite directions. That means that is whenever we insert a magnetic field, the magnetic field lines are associated with this coil are varying. That is, when we move the magnetic field, the magnetic field lines may be varying associated with this coil, and this variation in the magnetic field induces a current. Okay, so the direction of the current depends on the direction in which the magnetic field lines are changing. Okay, so when we insert the magnetic field, the current is produced in one direction, and when we take out the magnet, the current is produced in the another direction, the opposite directions. Okay, and is Michael Faraday. You can see in this figure also the above the facts we can see. The magnetic when the magnet is plugged into the coil, here the magnet field lines associated with these coils are changing, are crossing, so there is a variation in the magnetic field, so current is induced. When we take it out, the current is induced in the opposite directions. So Michael Faraday, he studied well about this electromagnetic induction, and he summarized some laws that is known as the Faraday's laws of electromagnetic induction. Okay, here the first law. The first law is states that whenever the magnetic flux associated with a circuit changes, an EMF is induced in the circuit. Whenever the magnetic flux associated with a circuit changes, an EMF is induced in the circuit. That we already discussed. And the second law, Faraday's second law states that the induced EMF produced in the circuit is equal to the rate of change of magnetic flux through it. Here we have a magnitude about the induced EMF. Here, according to the Faraday's second law, here the induced EMF is equal to the rate of change of magnetic flux. That is, E is equal to, suppose phi is the magnetic flux through the circuit, then E is equal to d phi by dt. So that is the Faraday's second law, and it gives an idea about how much is the EMF induced during this electromagnetic induction. Now let us see when a electric charge is placed in a electric field. Obviously, there is a force acting on that charge. Suppose Q is the charge, it is placed in an electric field of intensity E, then the force acting on the charge is equal to F is equal to Q into E. And also, when a charge is moving in a magnetic field, the charge also experiences a force. Okay, so in a magnetic field, if a electric charge is placed, it is placed at a rest in a magnetic field, then there is no force. But when a charge is moving in a magnetic field, then it experiences a force. That means here the magnitude of this magnetic force is given by F is equal to Q into V cross P, or Q is equal to, or F is equal to QVB sin theta. The magnitude of this force is equal to QVB sin theta. So here what is Q is the charge and V is the velocity of the charge. That is, the charge is moving in the magnetic field, and B is the intensity of magnetic field. And what about theta? Theta is the angle between the direction of magnetic field and the direction of velocity. Suppose in a region where both magnetic and electric field are present, and suppose a charge is moving in this region, so it experiences both the electric and magnetic force. So the total force can be on the charge is the sum of these two forces. That is, F is equal to F electric plus F magnetic. So what is F electric? That is QE plus F magnetic is equal to QVB sin theta. So that is total force F is equal to QE plus QVB sin theta. And this total force is called the Lorentz force. The Lorentz force. Now, suppose a current carrying conductor, when a current carrying conductor is placed in a magnetic field. So in the figure you can see, here we have a permanent magnet, and we suspended a conductor with some arrangement, and the two ends of the conductor is connected to an external source of EMF. When we insert the key, that is, the current is flowing through the conductor. So now this current carrying conductor is in a magnetic field. So when we switch on the circuit, we can see a deflection, a movement in the movement of the current carrying conductor. That means in the magnetic field, when a current carrying conductor is placed in a magnetic field, when a current carrying conductor is placed, it experiences a force, and the magnitude of the force acting on this current carrying conductor in an external magnetic field is given by the relation F is equal to BIL sin theta. F is equal to BIL sin theta. Here, the B is the magnetic field, intensity of magnetic field, and I is the current flowing through the conductor, and L is the length of the conductor, and theta is the angle made by the length of the conductor, the direction of the conductor, the direction of the current, and the direction of magnetic field. Okay, so this is the magnitude of the force. Now, in which direction the current carrying conductor is moving? Now, that is given by we have to memorize the direction, we have a rule that is called the Fleming's left hand rule. So, what is the Fleming's left hand rule says? So, we take our left hand and stretch the three fingers. Which are the three fingers? The thumb, the forefinger, and the middle finger in a mutually perpendicular directions. Suppose the forefinger pointing in the direction of magnetic field and the middle finger pointing in the direction of electric current, then the thumb will give the direction of force acting on the conductor. So, thumb will give the direction in which the conductor is moving. So, using the Fleming's left hand rule, we can easily find out the direction in which the current carrying conductor moves, or the direction in which the force acts on the current carrying conductor. So, that is the Fleming's left hand rule. So, we remember that here the force acting on the current carrying conductor is perpendicular to both magnetic field, the direction of the magnetic field, and the direction of the current.